And this year, in 2018, the Test of Time Awards Committee chose to honor 6 papers. Out of these 6 papers, we are honoring 2 of them, the 2 marked in red, at this conference here at MobiCom. The other papers are honored at other SIG Mobile venues based on the author's preference. So it's with great pleasure to announce the Test of Time Award for the paper Modeling TCP Throughput, a Simple Model and its Empirical Validation by Jitendra Padya, Victor Firu, and Don Tousley. This is a paper presenting a TCP model, and as the committee described in this award citation, it's arguably the one that significantly influenced the SIG Mobile community. It's not only elegantly simple, but also capable of accurately predicting TCP throughput over a very wide range of loss rates. And after 2 decades, it is still taught in several networking classes and often used as the starting point for modeling research. Please welcome Don Tousley. Congratulations.
Thank you.
Clicker.
Okay. And, I have to say we're really very honored and excited to, let's say, be getting this award. It's certainly not something that we ever expected, given that, in particular, the paper wasn't published in any of the SIG Mobile conferences. And I think it does SIG Mobile great credit that they sort of are willing to sort of recognize papers outside of their conferences. And I should mention this work was done all at UMass. Of course, we've all sort of spread around since then. And what I want to do is to sort of start sort of reflections on this work. I want to, there's a question of why did we do it? Then I just want to say what the result was that appeared in that paper. And then Victor Feroiu is going to come up and talk about how we went about doing this, because I think it really is a wonderful example of, let's say, science. And there are a number of lessons that we'd like to sort of impart that we've taken away and that we think is useful for the community. So it starts off with sort of at that time, there was a lot going on in networking, and the Internet Engineering Task Force had sort of decided that there was going to be a notion of TCP friendliness that protocols had to adhere to. And it was sort of mandated, that anything that you develop had to be TCP friendly. And at the time, the operating definition was that the rate that you got using a end-to-end transport mechanism should behave as this expression here, that basically it should be inversely proportional to the square root of the loss rate, the loss probability that the flow would encounter. And this was something that had been derived and sort of put forth. As I said, the IETF declared that it was imperative for everyone to adhere to that. And for a number of years, hundreds of papers were written that essentially said, well, this is what TCP friendliness is, and we're just going to accept it, and we're going to work with it. And I guess in sort of reading up on some of this work, we were a bit skeptical. Actually, to be honest, we started off, we wanted to cheat. we wanted to figure out how we could develop a protocol that would do much better than TCP, but would be considered TCP friendly. And so the decision was made that we ought to do some measurements to see, in fact, how TCP works. And what we discovered was that it didn't adhere to this particular formula. And so I'll tell you what the result of the paper was. It was basically a formula that essentially tried to correct for that. I'm showing you a very simplified version. Victor thought I should have put up the entire formula, but it's really, it's a bit on the ugly side. And you see to the right a couple of result graphs that essentially show measurements that we made at the time, to Europe, within the US, and plotting the throughput that was obtained as a function of the loss probability. The green curve is the 1 over square root of p formula, and you see that the data just does not match that. But when we came up with this final result, we had a very good fit with the data that we were collecting. And so we published it in SIGCOMM and thought nothing of it. But then what we discovered over the years was that people took the work seriously, and they started doing measurements in completely different environments than the ones that we had assumed when we were developing the model. In particular, they were looking in wireless settings where losses are very, very different. They can be due to noise and not due to congestion. And they were finding that the formula was actually very accurate. And so that was really very pleasing. TCP has evolved over the years, and so for the most part, the formula has been relatively insensitive to the version of TCP, something that we also didn't expect or would not have expected. And actually, I should mention one of the things that I found really interesting at the time was that the model sort of predicted the behavior of TCP in the wild much better than it did in an NS simulation. And I keep thinking, and I've talked to my co-authors, if we had used NS to validate the model, we might very well have come up with a different result, one that would not have done as well looking at things in the wild. And then, as I mentioned, what has proven to be the case is that the expression that we derived really is very insensitive to the loss process. It can be a very deterministic loss process. It can be bursty, but the model seems to capture the underlying behavior well. And so what I'll do now is I'm going to turn it over to Victor, who is going to talk a bit about how we went about coming up with this result. Come on up. This is...
Yep, thank you. Thank you, everybody, and thank you, the organizing committee and SIGMobile for this award. We're deeply honored, humbled. In our wildest dreams, we wouldn't have expected this. So just wanted to share with you just a couple of things that remained with us over the years, and hopefully a little bit of lessons learned for the new researchers that are just coming up in the field. Don nixed the ugly formula, but could not nix the ugly picture. So, we need an ugly picture to understand what was behind. So that was actually the underlying principle that we used throughout this research. Try to understand, not just fit things to whatever the experiments were showing us. Very briefly here, we tested the model that was already proposed by previous papers and was coined by the IETF as the TCP friendly that Don has shown previously. That was the additive increase, multiplicative decrease. We show from many experiments that was quite far from what was seen in the wild. So we started, the underlying principle for us was to treat this as a decomposable, if we could, a decomposable complex phenomenon and decompose it into some kind of a separable, understandable parts. I show here just the three main pieces that put together are responsible for the most of the model. Mind you that the protocol is much more complex than these three parts. Without saying the very last part of the behavior, which is the behavior of TCP above, loss rate of 4%, goes way out of the initial model that includes all this timeout back-off behavior that was not modeled before. And that actually was considered as being outliers, and previous papers actually discarded those results as being out of scope. Out of the many experiments, and G2, I would like to invite G2 to also say have some remarks here. Together we looked at the data, and clearly the data did not accept being thrown out as outliers. So that's how we got to actually try to understand, but that part was much harder to understand and to model than the first part. So this is, going away from the ugliness. There is beauty behind the ugliness, which is the approach that we took was the scientific method. It's easy to say it now, but it's not that easy to keep at it while you have no idea what's going on, and the system, the data is ugly, the data is complicated. Well, so we took this. Personally, I like to read about physics and discovery in physics out of experiment, and I consider this as a physical, although man-made physical phenomenon, and try to study it by experiments and try to model it using the scientific method. What do I mean by that is try to understand what's behind the data, what is the phenomenon, rather than matching whatever model formula to match as well as possible the experimental points. We wanted to have a model that actually reflects the parts of the protocol that are specified and we understand. I think we succeeded, and the reason, maybe one reason for being a lasting, valid model is that we modeled the actual design of and parts of the design of the protocol rather than matching data with some formulas. So why was that important? It was not just to model and to make it the new standard for TCP friendliness, but it impacted a lot more domains after that. For example, now that we understand how it works, doesn't mean it's the best that we can do. So there is a lot of research that came after to look at better ways to actually deal with congestion control. Another impacts were on wireless And you know much better than me right now the impact of wireless on the just regular TCP congestion control, how it could react badly, and what are the methods to actually mitigate that. Multicast at the time and for a long time has been a big topic, and doing congestion control in multicast was essential and as well as not established because all TCP was unicast. So that was once we teased out the congestion control for behavior and encoded it in this model, then multicast congestion control was able to take that and actually implement the first congestion control for multicast. This also opened the whole field of active queue management based on control theory, and that's another topic that I don't have to talk about now. So I think in lessons learned, it's really to be, first of all, as Don pointed out earlier, to be skeptical. These are Don's words, not mine, but I absolutely subscribe to that. Don't accept the party line. Be skeptical, test it, and if it doesn't fit, look for a better model or a better way to do things. So why was it? Obviously, we had some luck, but also combined with being at the right time in the right field. But being in the right field at the right time came out of actually following discussions on the timely topics. So this was a timely topic at the time. It seemed to be already established. The conclusion seemed to be already established, but we took the next step. Well, I don't want to repeat, but I will repeat myself here because I feel it's so important to talk about this scientific method, modeling and experimentation. They go hand in hand. Again, the model that I used, like the physics experimentation and drawing models out of experiments to basically build effectively a new law. Maybe this is one of the first man-made physics law that I'm sure that are many, and I believe that the future is going to be man-made reality with complexity that eventually will surpass the complexity of the physical phenomena, and we need to be prepared to be able to understand and apply the scientific method to that. I think I'm done with my remarks. I really wanted to thank everybody in the audience and the organizing committee. And I also want to say one word about graduate student advisors. If you like your advisor as a PhD student, please thank them. I cannot underscore the importance of the advisor in your future work as a researcher. And a good advisor is invaluable. Thank you, Don, and thank you, Jim Crows.
Thank you for sharing the story.